Take any
Hello,
questions.
everyone. My name is Anna Pusack. I'm a fourth-year graduate student working with Jessica Liu at UC Berkeley. I'm going to be talking about an object at the Galactic Center that I discovered using JWST data, but with only one epoch of spectroscopy and the oversubscription of that telescope, I really rely on the decades of Keck data, archival data, as well as continued observations taken along with the Galactic Center group here at UCLA. There we go. Before we get into the details, I want to put this object into the context of the Galactic Center for you all. Sorry, this is a JWST image, but I have plenty of Keck data, don't you worry. This gives us a good perspective of the different populations of stars that I'm going to be talking about. Inside the yellow circle is highlighted the nuclear star cluster, as captured by this NIRCam 3-color image. This is a dense region, cluster of stars centered on the supermassive black hole, Sagittarius A star, that is in the magenta at the center. Within the cyan circle, this is the young nuclear star cluster consisting of O and B population of stars, which is also the field of view of our JWST near-spec IFU mosaic, as well as much of our Keck imaging. And the object I'm going to talk about is within this cyan circle, and just east, north is up, east is left, just east of the Sagittarius A star, so within the general location of this young nuclear star cluster. So here's that spectra from JWST. On the bottom, you'll see the NRS1 detector from JWST. This is de-wiggled. If you know, you know. Using an algorithm developed at UC Berkeley by a postdoc there. It's still very much in its beta testing phase, but believe me, this is better than it was. You can see the H1 emission from the gas, as well as some bracket gamma and the CO band heads that I have marked here in emission, reproduced in the spectra above. These are the features that made this object stick out to me as I was looking through several spectra in the region. You'll see that the 3 12CO band heads are reproduced pretty well there. However, there are several other emission lines that we're still working to identify. These could be forbidden iron lines in some cases, but they would be at a different radial velocity than what I've determined from the CO. And we also see some helium features, and then ones that we cannot identify anywhere in the literature. So it's still very much an open question as to what this object is. As such, we have looked at a bunch of different kinds in the literature and we've sort of settled on it being a bright source within a disk. To get CO in emission, you need temperatures that are relatively cool but kind of hot, as well as densities that are pretty high. And so this works really well for an inner disk region around objects like young stellar objects, accreting binary systems, and even evolved star systems. One of the main ways that we can distinguish between the young and evolved stars happens to be around looking at the ratio of the 12CO to the 13CO. And with some quick qualitative viewing of the 13CO, it does seem to not have very much. So going on the assumption that it is a young stellar object, of which there are several categories. You can group them depending on a lot of different features. One of the ways is mass. T Tauri stars, we've heard of a lot already this week, are the lower mass end. And they can have CO in emission, but not always. We need sometimes a hotter star to really to get that CO to emit. And that's where the Herbig BEs and massive young stellar objects come into play. This on the right is a catalog of Class O protostars from a Legulic paper recently came out that shows very clearly a variety of sources that have CO in emission. These objects generally, but not always, also have H2, something we actually can't find in this Galactic Center object, and almost always have bracket gamma as well, which my object does, which I'll discuss next. And this is really where Keck comes into play. So we have several epochs of data collected by the Galactic Center group dating back almost 20 years. of the KN3 filter. And this gives us a nice view of that bracket gamma emission. And what you'll see here is that I actually see two lines pretty consistently throughout. All the yellow here are the Keck epochs. The blue is that JWST epoch. And the purple is from data mining into the VLT ARIS data, but it's really quite noisy and I have to do a little bit more analysis there. But you can see that there are two clear lines that pop out for this bracket gamma. One is a narrowband emission feature, which is likely the ambient environmental gas. And then there's also a broader line feature that corresponds quite nicely to the radial velocity that I found in the CO band heads. So what I had to do to get these was to fit a double Lorentzian line profile to each. This is where things can get messy. Not all of them look like this. This was probably the prettiest one that I wanted to show you all, where the narrow band is quite clearly distinct at a rest wavelength for bracket gamma, and then that broader feature not as bright and off at a different radial velocity. Let's see, how am I doing? 5 minutes, sounds good. So with these radial velocities, taking these with a grain of salt, that this is kind of hard to disentangle due to the ambient gas, we can see that there is a trend of about 280 kilometers per second in radial velocity, and there is some variation in the radial velocities that could indicate that it's a binary system, in which case we might explore some other avenues like low or high mass X-ray binaries, that sort of thing. However, those two data points are with probably the hardest to disentangle from the gas, so I would take those with a grain of salt. And if then there isn't much RV variability if you don't believe those. Looking at those two data points, they do correspond to some of the worst error bars on my velocity dispersion, so that sort of supports that idea that we need to do a little bit more careful diagnoses there. The velocity dispersion is around 100 kilometers per second, and this is something that matches very well with the literature quotes for young stellar objects. But Keck can give us more than just spectra. We also have quite a lot of imaging from NERC2, and we can see with this object that there is, through 4 bands in NERC2, H, KP, LP, and MS, that there is variability over the last 20 years, as well as a steady rise to get brighter. All of these sorts of things are things we generally see with young stellar objects. There's a lot of variability anytime you really have a disk, so this might not necessarily deviate there. If we look at one of the CMDs, we can see that there's a broad spectral range and temporal coverage in color. We can see how the object appears to be getting bluer if you follow the timeline in the color magnet or the color bar on the side. It goes from blue in the color bar, but it's going into appears to be getting bluer as well, and then maybe back to red again. This may have something to do more with the environmental features of the object. It is in quite a dense gas region called the mini spiral. If I, however, plot it with some synthetic isochrones made by Spicy, we can see that it is far off to the red side of the CMD that will tell us that it's perhaps more in the young stellar object, the protostar, still developing this part of the spectra, or part of the HR diagram. If I were to try and plot a isochrone with even more extinction, I'd need at least 4 magnitudes of extinction to get a star to fit it over on that side. And you can see a similar thing in other colors as well. If we take all of these magnitudes and another diagnostic that you can use for young stellar objects is to look for IR excess. And we do seem to see this with plotting quite a few different spectra, again, using the package Spicy, that there is color excess in the L and M off of the stellar spectra you would see here. This, if you look in the literature, is consistent with work by Linda Hillenbrand on Herbig BEs, that intermediate mass young stellar object. And we would need quite a few more different bands, mid to far infrared, to do a comprehensive disk model, but it is there. We are leaning more towards a star plus disk with this flattening off on the side off of our spectra. So this is work that is still in production. We're leaning towards a young stellar object, likely a Herbig BE or a massive young stellar object. This works very well inside of the young nuclear star cluster where we see many massive stars at a very young age. There's several things still to do. However, if it is a young stellar object, the presence of such an object still growing in its protoplanetary disk favors a younger age than what we've currently quoted. But again, more analysis is needed.
Hello, everyone.